So our final speaker of this session will be Matthias Bock, who's going to tell us about spin squeezing and entanglement generation in iron crystals.
Yeah, thanks a lot, Ryan. Welcome to my talk. I know it's quickly before lunch, but I hope I can catch you still for 20 more minutes to talk actually about some very recent results here from Innsbruck. So I'm an iron trapper there in the group of Christian Rhode, and we look into two-dimensional iron crystals for quantum simulation. And since I think this is the first iron trapper talk in this conference, maybe let's take a look how we usually do quantum simulation. So if you hear iron traps, then you might expect such a linear string here, for instance, or some CCD architecture. And usually what we take here is then we have this string, and we say, okay, we can encode in this some isomodel model physics. So each ion here, we take some qubit, an optical qubit, a hyperfine qubit, and we encode a spin 1/2 particle in this ions. And then what we do on top is, let's say, and this is an example for calcium-40, where we have a great history in Innsbruck. So you see here 3 important levels. So we have a S to P transition, where we can scatter a lot of photons. So this is great for fluorescence readout. And we have a very narrow band transition here between S and a metastable D5 half state with a lifetime of a second. And this we can then use to encode an optical qubit here addressed by a narrow band laser. And if you combine this with the fluorescence readout, we can say, okay, if we see some photons, then we're in the ground state. This is our zero or our spin down, and the other one is spin up. And if we add then some lasers to globally and locally control the quantum state of these ions, then we can indeed encode some Ising model. But how does this work? So the ions are a few microns away, so neighboring ions don't care if the other one is in the S or in the D state, but we can make use of the fact that the ions are in a single 3D potential, and this gives some normal modes. And these motional modes we can actually use to mediate some interactions between the ions. And this is shown here. So what we usually call the carrier transition, this is our qubit transition. And you see on the lower and the higher energy side, you see these so-called motional modes. So let's say these are the normal modes, which are actually purely from classical calculations. And this corresponds basically to the fact that you add or remove a phonon out of these motional modes. And what we do then is, that's a bit now magic, so you have to trust me. So we usually shine in laser beam, which is here a bichromatic laser beam, which has 2 tones, and we drive off-resonantly all these motional modes here, and this gives us then, after some math here, actually an Ising-type interaction, where we have here this Ising Hamiltonian with the sigma x term and a tunable coupling strength, Jij, and a transversal field here. And what is really nice in our platform is that we can control these parameters by just setting these laser parameters. So for instance, the Jij usually follows a power law interaction, and by changing, for instance, the tuning of these laser beams with respect to the modes, we can make it very long range if we go close to the modes, and very short range if we go far away from the modes and talk to all modes, basically. And also this B field can be tuned, and we can go to different regimes. So for instance, to small B fields, where it's really an Ising-type interaction, but also to large B fields. And this is then usually this XY regime, where if you go to the interaction picture, if B is much larger than J, then you suppress correlated spin flips, and you go to some flip-flop interaction, which we usually call here the XY. And this has been explored, let's say, in Chris Monroe's group when he was mainly still in Maryland. Now I think they moved these experiments, and also in Innsbruck, in this analog fashion, but also, let's say, some recent interesting stuff from Continuum. I think this is a more digital approach, but I think they can also do in similar things, but with a very different architecture. Now the question is, okay, or we thought, let's say, we want to extend this to 2D, and there are actually 2 reasons. One is a very practical one. So if you look at these linear strings, then usually you never see more than 50 to 100 ions. And why is this? Because if you want to get such a linear string, you need to make this radial confinement very strong and the axial confinement very weak. Because if you make the axial confinement too strong, then you get some zigzag configuration. And this actually showed to be that this causes quite some troubles, actually, because the weaker you make this axial confinement, the more heating you get, so thermal phonons which leak into your motional modes. And also addressing single ions becomes challenging. And this is actually nice in this 2D architecture, because at much higher in-plane frequencies, you can get more, let's say you can accommodate more ions on a smaller footprint. And the second one is, I think, and this is maybe more a thing for Ryan, actually, he's an expert on this. Of course, all the spin physics is way more interesting in 2D, and this is maybe some natural motivation. If you now look, then actually there exist some experiments in 2D. So there's this great panning trap experiments from NIST, from John Bollinger's group, also in Mike Bierchuk in Australia. But the challenge there is, let's say you have a pending trap and you can accommodate there a few hundreds of ions, but the challenge there is that these crystals rotate at a very high speed with about 30 to 40 kilohertz, depending on the parameters. And this makes actually single ion addressing and also imaging very, very tough. And also these modes are super hot and leak into each other, so this is actually very challenging. We don't want to go into pending traps. This is not, I would say, what is done in Innsbruck usually. Another idea would be, let's say, to use some micro traps or some surface traps. However, there the fabrication of these traps is really challenging. And until you get a trap with significant lower heating rates, what is currently possible, I think this is, expense more than several PhD generations. So our approach is, okay, we want to use something where we are good in, and these are, let's say, these usual linear segmented Paul traps. And this Innsbruck design, let's say, which exists now for 20 years or 25 years since Rainer Blatt is there, is that you have this design here with two Rhode electrodes. Two of them are supplied by radio frequency field. The other ones are at the DC potential. And also you have the end cap electrodes to generate the axial potentials, which is also DC. And actually you can create a 2D crystal in this. So if you increase here the potential on these blue electrodes, then let's say what happens, you undeconfine them in the RF direction and you automatically get a 2D crystal. However, the problem there is that, as you can see here, the direction where we want to image or address these ions, this is blocked here by these electrodes. And the even bigger problem, and this is maybe more for the ion trap experts, this is the usual enemy in Paul traps, is so-called micromotion. Because only if the ions are on the high symmetry axis of the trap, then you can consider this as a purely harmonic potential. But as soon as they move away from this point, then you get an additional driven motion from the radio frequency drive of the ion trap. And this is actually a big problem because this is a significant movement. It's very painful in optical atomic clocks. It's painful for laser-based gates. And this is also unavoidable in 2D crystals. So we thought, okay, is there some way around? And we came to the conclusion, okay, we have to live with this, but we use a trick here. So we change a bit the design of our trap. We basically split these electrodes, which are somehow in the way to image the crystals, and we also split these end cap electrodes into 8. And what is the benefit? The first benefit is that you have now here space to image and address the ions perpendicular to the crystal surface. And the second advantage is that you can really rotate or orient this crystal, that the micromotion is just in this direction. So you see here this arrow, this is the direction of the micromotion. This means that the motional modes which are perpendicular to the crystal, you can make these modes free of any micromotion. So they behave naturally, they don't heat up because of this micromotion. And this gives us really the possibility to use these modes for simulation or for computation without having the micromotion. We live with it in the plane, but this is not so harmful for us. And actually, that's a report which came up a few years ago, also by many other groups, and that's how it looks in our case. So we have such a monolithic trap here. If you want to know about it, you can read this paper or reach out to me. I don't have too much time. It's also, let's say, very technical ion trap physics, maybe not suitable for everyone here. And but what we can do is we can really routinely trap, cool, and control 2D crystals with up to 105 ions in our trap. And actually also other groups explored this here, for instance, Kivan Kim and Tsinghua, Phil Rich and me here in Indiana. They have some nice results, and maybe the most impressive in terms of ion number is currently what Lu Ming Duan achieved here in Tsinghua University, so they can really trap here 500 ion crystals in a cryogenically cooled ion trap, but with similar design actually as all the others. And so let's start to look how we can implement some quantum simulation here. And our qubit actually is in this case a ground state qubit here, which has the advantage, it's not what is usually done in Innsbruck, but this has the advantage that we don't have any spontaneous decay at the cost of a much worse coherence. So this is very sensitive to magnetic fields, but we were able to shield our experiments very well from magnetic fields, and with this we can get some decent coherence times of a few hundreds of microseconds. With some echo pulses we can even go beyond this. So this is sufficient at least for what we do. And we can also drive this qubit with a global Raman beam. So you see here you have this Raman transition, and we have a big global beam, and we can here drive, for instance, what you see here are Rabi flops from a single ion out of a 91 ion crystal. And you see this works decently well if the ions are cooled. I will explain this in a minute. And we can also do some composite pulses for global rotations with, let's say, error here in the range of 4 times 10 to the minus 4 verified by randomized benchmarking. And this is, let's say, global manipulation, which is well suited to implement some entangling interactions because we can couple to the motion, but we also would like to have some single side control. And this we achieve here by a tightly focused laser beam, which we can steer here over the crystal by using acousto-optical deflectors. And here you see such a typical scan. So we have this trace beam, and we steer, for instance, in horizontal direction, works same in vertical direction. So you see we can here excite all the ions, and also with sufficiently low crosstalk here of about 2.2%, 0.5%, depending on if you look over the whole crystal or only to the nearest neighbors. And this gives us actually the possibility to do sigma C gates by using a Stark shift. So Stark shift, actually, if you apply it for a certain time, it's nothing else than let's say, a well-controlled sigma C rotation. But we can also do some resonance stuff. So for instance, we can here remove selectively some ions out of the computational subspace by moving them to this metastable D level and by parking the ions there. And with this, we can, for instance, create here this fish, which has maybe scientifically not a great value, but it's nice to look at. Maybe somebody has an idea what we can do with this. What is nice, right, that this is also that if you look at let's say, some single shot pictures with a success probability of currently 0.8, we can push this a bit by some automation, but we can, let's say, in most of the cases, we get actually this configuration. So far, so good. Let's take a quick look at the motion. So now we have our qubit, we have some single side control, but we also need the motional states. And we would like to have them in a well-controlled state, which means close to the motional ground state. And that's, again, something for the ion trapping experts. So we make use of a very nice multi-mode cooling technique here, which is called electromagnetically induced transparency cooling. And we can, in a very short amount of time for ion trap physics, so 300 microseconds, really cool all the modes close to the ground state. So you see here some spectra on the red sideband, and here without this ground state cooling, you see that we can still excite on the red sideband, so we are not in the ground state, but with the EIT cooling, then we highly suppress this. And if we do some thermometry, then we really see, okay, we are here in the range of 0.1 phonon. And additionally, we made sure that the whole electrical environment is very clean, so that we get simultaneously some very low heating rates of 0.5 phonons per second per ion. And also we can stabilize, let's say, these potentials, so the modes don't wiggle around, but they're really, really stable over time, so that we get decent coherence times here of these motional modes of hundreds of milliseconds. Okay, with this, I think we have all the ingredients ready to implement the Ising model. And the first thing which one would like to look like are, let's say, the spread of global of correlations here. So what we do is we prepare all ions in the down state, and then we do global quench with the Ising model, in this case without any magnetic field. And we measure here correlations between the ions. This has been done here in Chris Monroe's group for linear chains, but it also works here in these 2D crystals. So for instance, we can look over time the correlations between this left ion here and all the others, and then you see here nice that these correlations build up, and after some time they disappear again. And to look a bit more quantitatively, the nice thing is that this can be simulated very efficiently, classically. If we take our motional modes, if we take our laser parameters, and we calculate the JIJ matrix, so our interaction matrix, and then we can very well calculate this. And as you see here, for some selected pairs of ions, you see here these correlations over the interaction time, and this, let's say, agrees really well with the theory. So we have, I believe we have some good understanding of what's going on here. And this is now for a very long range case here where the alpha is about 1. If we now go to short range, that's actually experimentally more challenging because you have to fight against decoherence. But even there, I would say, the overlap is still sufficiently okay. And for instance, for this case of alpha equals 2. So that's usually what we refer to as global quench. We can also do this locally, which means we prepare all ions in the down state, then we flip, for instance, this central ion here, this red one, and then we evolve this system under the XY Hamiltonian, so in this case with a magnetic field, with a strong magnetic field, and then we measure afterwards the single side excitations. Again, this is very easy if you restrict yourself to a single excitation, and if you look then at the dynamics, this is actually some quasi-particle dynamics governed by magnons or by spin waves. And as you see here, again, we have a good overlap. This red one is this single spin, which is in the beginning in the one state, and this spreads into this crystal. And you see here nicely these oscillations coming from these quasi-particle interactions. So this is also, let's say, somehow satisfying. The question is now, okay, this looks nice, but can we create on top some entanglement? And if yes, how can we verify that we have some entanglement? And let's say motivated by some recent work in our linear chain, we thought a good point to start with is looking at spin squeezing. So spin squeezing is something which is motivated from metrology, where you want to use some phase sensing with atoms or ions for the purpose of atomic clocks, because usually what you can get, or usually if you look into such a scenario, then the uncertainty of the phase estimation scales with 1 over the square root of n, and you can enhance this using quantum mechanics to 1 over n, which is called the Heisenberg limit. That's very challenging, but spin squeezing lies somewhere in between, and it's possible, it's much easier to create this compared to the Heisenberg limit, where you need somehow GHZ states. And we can actually do this, so how you would usually do this, or how it's often done, is by using the so-called one-axis twisting, using this Hamiltonian. And as you can see, that's similar to what we have, but this is a purely all-to-all Hamiltonian. What we have usually is, however, this power law Hamiltonian. But it has been shown here by our theorists from Boulder that if you now work in this XY regime, then you can recover this, because, let's say, the power law Hamiltonian would not preserve the magnetization, but in this XY regime, you preserve the magnetization, and this stabilizes the creation of these spin squeeze states. And there are some recent experiments in this direction from our linear chain, also from Adam Kaufman, Antoine Prouvaire, Monica Schleyer-Smith in Stanford, who used somehow this protocol or similar protocols to see the spin squeezing. We thought this is a good starting point. So what we do is we prepare all ion in the equatorial plane. Then we apply our indirection to squeeze the state. And afterwards, we measure here the variance and the Bloch vector length to estimate here. This is the so-called Vineland parameter, and this is a good measure for the spin squeezing. And what we see is, so we get some decent results out. So this is the Vineland parameter versus the interaction time. And you see here the optimal interaction time of a few hundreds of microseconds. Oh, this is microseconds, not milliseconds, sorry. We get here about minus 6.2 dB of spin squeezing. Interestingly, and you see here the, let's say, respective histogram, where you also see that the variance indeed goes down for the squeeze state. Very interestingly, it still works with this Ising interaction, which does not preserve the magnetization, but in these 2D crystals, actually, we have a better connectivity, and this somehow is also advantageous for this. So you can even use this Ising interaction, although it has not the same amount of squeezing, you can still use it to generate some squeezing. And we can go also a bit beyond this, so by using some variational optimization. So you can imagine you can play around with this squeezing ellipse on the Bloch sphere and rotate it and squeeze further. And it has been shown here in these papers that if you use these multi-layer sequence, that you get even higher values of spin squeezing. And we can do this. We can use some variational optimizer from the Solar group, which is somehow a global optimizer and finds the best parameters for these rotation angles and the interaction length. And with this, we get here about 7 dB of squeezing, even in a 19 ion crystal. This also works with 91 ions. So there you see we get here a bit, almost to 11 dB of spin squeezing. And you see here the theory curves. These are actually calculations from our theory friends for a noise-free model. And you see we are quite close, so not completely there, but quite close. And we are currently rigorously evaluating all our error sources so that we can understand or that we can even include them in the model and that we get a good overlap. So this is somehow satisfying. The question is now, okay, what happens if you go beyond this optimal point of squeezing? And what has been shown here in this paper here in our linear chain experiment, then you get to a non-Gaussian regime. And eventually, if you evolve it much, much further, then you end up in a state which is very close to a GHZ state. And this is what we see here. So we can look, okay, can we create also GHZ states with the protocol? With this protocol, the answer is yes. So up to here, a number of, let's say, a bit around 20, this is this red curve, we can indeed create GHZ states without any spectrum correction. So this is really in the raw data. And for comparison, we also looked at if we move the laser tones very close to the motion mode, so we get close to an infinite range interaction, not at all, but it's very close, then we can get here a bit better because the interaction gets shorter. But we have to fight, of course, the other modes. So this is full of coherent errors, but it's still nice to see. What's missing is the last data points, data from last week. So the 32 qubit was slightly below 50%, but I hope I can push it to about 50% for 32 qubits. Yeah, with this, we have some further plans. So we would like to improve, or let's say improve our methods to do quantum state verification by upgrading the system, that we can also do the SIG PUVM readout combined with classical shadows, or also this randomized measurements, so that we have more let's say more tools analyze states, and in the long term, we really want to explore then this 2D spin physics. Yeah, with this, I would like to thank you. Here's our team in Innsbruck, guided by Christian Rose, and these are our theory collaborators from Anna Maria Ray and from Peter Solasto by Chilla in Innsbruck. And with this, I would like to thank you for listening.
Thank you for the very nice talk. Questions? Let's start there.
Yes, thanks for the nice talk. I just want to clarify, in the last plot you showed, like there's a fidelity and the GC state. Like, do you expect it to reach the Heisenberg limit? And also, like, there seems to also be a stronger squeezing at the optimal interaction point. Like, what is the asymptotic scaling? Like, do you have a
So let's say with these numbers, you are maybe at the Heisenberg limit until something like 9 to 10 qubits. If you go beyond, right, then the parity fringes push it away from the Heisenberg limit. So I think until 10 qubits or so, it's close to the Heisenberg limit, but not further.
Okay, thanks.
Yeah, and this is not expected to be at the Heisenberg limit. So this has a different scaling. Yeah, but that's hard with squeeze states. So there are some protocols, some time reversal protocols where this might be possible, but it's in general hard to approach the Heisenberg limit. Yeah. So you really need high fidelity GHZ states, I think.
What types of techniques do you have to, for example, deform the array as you're doing the simulation? Like, for example, expand, contract. Are these types of things that are tractable?
Well, in this we are unfortunately very inflexible. So these eintraps work best actually if you keep the parameters super constant.
I see.
Because as soon as you start to change things, it takes very long to thermalize because we're sending many watts of RF power into it. So in this sense, it's very unflexible. We can do with the stress beam here some stuff like this. This is possible, but I would say apart, that's it in terms of reconfigurability. Yeah, unfortunately. That's the downside of science.
Any last questions? Okay, if not, let's thank Matthias once again.